Good morning. This is Jimmy Youngblood at Somax. I want to thank everyone for joining us today on this webinar. The objective of this webinar and the webinar series is to get information out to the industry, especially as travel is very limited. I also want to thank the speakers, Abigail and Sean, for taking time out of their busy schedule to present on these topics. I would like to introduce each speaker and the company they represent for your information at this time. Abigail Gilson, MS and PE at Tiein Environmental. Ms. Gilson spent the first part of her career as a containment facility design engineer and joined TRI in 2012 to focus solely on the implementation and innovation of electrical leak location technologies. She has over 16 years and 170 million square feet of electrical leak location experience, as well as contribution with numerous published papers, seminars, presentations worldwide, and leading ASTM task groups on matter at hand. TRI is a world-renowned independent testing laboratory unaffiliated with any manufacturer or engineering firm. It provides testing, certifications, research, equipment development, and consulting on plastic materials in civil, environmental, and geotechnical applications. Sean Callandine, HGI Hydrogeophysics Incorporated. Sean is a geoscientist and the development manager at Hydrogeophysics Incorporated with more than 15 years of experience in geophysical and electrical leak location technologies. His expertise encompasses leak location projects at the Hanford nuclear site, in the mining industry, and many other industrial complexes worldwide. Sean contributes to many presentations and has published papers on geophysics and leak location technologies. HGI is a solution-oriented geophysical consulting company and service provider to the environmental, engineering, groundwater, mining, oil and gas, and natural resource exploration industries. HGI specializes in applying 3D geophysical methods and time-lapse subsurface monitoring of fluid through geological materials, leak detection, and liner leak location. As a reminder, we will address questions at the end of the presentation, and this webinar will be recorded and available on all three of the participating companies' websites for viewing. Abigail, when you're ready.
I'm Abigail Gilson, and Sean and I are going to be discussing the fundamentals of covered geomembrane surveys today. So the first thing you need to understand is how current flows through a medium. This is a plan view of a current injector. So picture a stake pounded into a soil layer, and we're looking at the soil layer from above. So this is a plan view of the soil. The plus here is the current injector, and current radiates out from that current injector. And what that does is it creates equipotential voltage lines perpendicular to the flow of current. These voltage lines get very tight as they approach a location of either a current production or a current draw. So this is what it looks like if there's a leak in a survey area. We have our current injector, and the current's flowing out from the current injector, and it's flowing into a leak in the geomembrane. You'll notice that the current is very tight between the positive and the hole. This is because, in general, current is going to follow the path of least resistance. So it flows everywhere and anywhere, but it will tend to flow preferentially where it's easiest for it to get from the current injector to the current return. It's easiest to visualize the current flow by thinking of it as flowing like water. So when we charge a survey area with voltage, it's like filling a reservoir with water. And then if that reservoir has holes or outlets, it's going to slowly trickle out of those holes and outlets. So the voltage potential lines end up looking like a topographical map that corresponds with the hydraulic surface elevations. So in this diagram here, we have our positive electrode. This would be a voltage high point, and our voltage low point would be where there's a leak. We have a dipole operator that's reading the voltage potential lines from the surface. So the leak is going to look like a bullseye centered around that leak location. There are actually several methods for testing covered geomembranes. There's a monopole where you have a roving single pole on a long cable with a static reference electrode. And this is going to produce a voltage map that's a lot like a topographic map. And then we have the dipole method, which is the most commonly used. The reason it's the most commonly used is that, frankly, it's the most effective. We'll talk about why in a couple slides. It's also the only method with an ASTM standard practice associated with it. In fact, there are two of them, and I'm going to be talking about the differences between the two of them in the next webinar. There are also some advanced geophysical methods that are proprietary. So we have really deep soil fills, we have buried tanks, we have deeply filled ponds that Sean's going to be talking about in episode 4, and then we have the permanent monitoring systems he described last time. So for me, the covered geomembrane methods just means the dipole method because that's the only method that I perform. To Sean, it means the dipole method plus some other proprietary methods that he will be talking about later. This is a picture of the dipole method being performed. It gets its name from the apparatus that's used to measure the voltage potential throughout the survey area. Dipole means two poles or 2 points of contact with the surface where measurements are made. We often refer to the front one as the front foot and the back one as the back foot. You'll notice there's string lines placed throughout the survey area. You must survey in a grid pattern throughout the survey area. If you don't have GPS guided system, you'll need these string lines. Even if you do have GPS, you still need the string lines if you don't have a GPS based guidance system. So the dipole apparatus is not measuring absolute voltage like the monopole would measure. It actually measures the voltage gradient, which would be like on a topographical map, that's like measuring the slope of the surface of that map. Rather than getting an absolute elevation, you're getting an elevation differential so that you can tell whether the ground is sloping downward or upward. So leak locations are like sinkholes. They're low points in the topography. So as the dipole travels across it, you're going to get a downward slope followed by an upward slope as you travel past that leak. I use an internal convention of measuring from the front foot to the back foot because otherwise it won't make any sense when I say downward versus upward slope. You have to have a standardized reference. So I'm always going to refer to the dipole measurements as being measured from the front foot to the back foot. To help you understand how to read a map created by the dipole method, it's easiest to show what that same map would look like using a monopole. So this is a map of the same survey area using a monopole versus a dipole. On the left, we have a monopole, and the color scheme that I use is for a given range of voltage. The highest starts with the color white and goes to yellow and then green. Then it changes to red and then blue and then black. So the white here, where the current is coming in, is the highest voltage. Where the leak is the lowest voltage. Over here on the dipole map, I adjust the colors so that it changes abruptly from green to red as the voltage goes from positive to negative. So this brown line you see here is like a 0 voltage line. The white here in the corner where the current's coming in is the highest positive, and then it goes to yellow and then green for less positive. And then as soon as it goes negative, it switches to red, and then it goes to blue. So this map on the right here was taken by a dipole traveling down and up on this survey area. So as the dipole approaches the current injector from bottom to top, you have positive voltage values, because it's kind of like walking up the hill to where the current is coming in, the highest being when it's near that current injector. As it's walking from bottom to top, as it's approaching a leak, you actually start to see the downward slope of that voltage map. And you get a maximum negative when the front foot's on the leak, and a maximum positive when the back foot is on it. So seeing these two maps side by side explains why the dipole method is considered to be a little bit more sensitive, because it's just easier to see the slope of the ground, and as it starts to go down, you can see it from much further away. Rather than looking at just voltage potential, the values are kind of meaningless. It's hard to decide where the cutoff is, like how low is low for a leak. What we really want to do is see the signature of the downward slope followed by the upward slope, and that is really how we can tell where the leak is. So going back to our water analogy, I have a water surface here around a leak location. What happens when you pull the plug out of the bathtubs, it creates a funnel in the hydraulic surface. So this is what the hydraulic surface would look like. This up here, this bullseye, is what the voltage potential would look like in plan view with something like a monopole. So the dipole is measuring the surface. So as it starts to approach a leak, it detects a downward gradient or a negative voltage value. And this value gets larger in magnitude as it gets closer to the leak because the voltage contours get tighter and tighter as it gets close to that leak location. So this slide shows a plan view of the voltage potential lines and what the dipole actually measures in terms of voltage as it travels across the leak location. This traverse is right across the leak, so one of the feet is going to hit the leak. So as it travels across the voltage values, you see the 0 right here. So this is a negative voltage range. The magnitude of the negative voltage is going to get very sharp right when the front foot is over the leak. So you're going to have the most negative value when your front foot's on the leak. Then it's going to pass through 0 and you'll get the highest positive when your back foot is over the leak. And then that positive value will taper down to background values. This slide shows what the dipole traverse looks like when it's slightly off of the leak. So the voltage values, you can see the curve is a lot softer and the magnitude of the signal is not as big as when the dipole is directly over the leak. What this does is this allows us to pinpoint the leak and get right on top of it because we move back and forth until we find the strongest negative and positive sign change in the voltage values. So this is a voltage map created by the dipole method. The dipole is traveling from bottom to top of the map. The current injector is located here. So what the current injector does is it roughly divides the survey area in half, and it has positive values on the bottom half of the map and negative values on the top. And when you're looking for a leak, you're looking for something with the opposite polarity of the current injector. Current is coming in at the current injector and going out at leaks. So leaks tend to look like a little butterfly on its side with a little bubble of negative below and a little bubble of positive above, separated by tightly spaced contour lines. So we have a fairly large leak signature right here and a little bit smaller leak signature right there. This is a double dipole. It actually has a dipole on the left and a dipole on the right. And it has not only GPS-based data acquisition, but it also has a GPS-based guidance system. So you notice there's no string lines in the survey area. So this unit creates a local coordinate system and it guides the operator virtually. So they're just following along the y-axis of the survey area. When you have a guidance system like this, it saves time in laying out those string lines. And when you have GPS-based data acquisition, it's much easier to get much better resolution for survey areas that aren't square or rectangular. So if something is shaped like a big amoeba, you can just go off your line and record data points as necessary. If you're stuck surveying along those string lines, you're only going to be collecting data along those string lines. Now I'm going to talk about how to prepare a survey area to be electrically tested. Current is always going to travel the path of least resistance. So if there's an access road in place or anything that allows the current to flow outside the survey area, it is going to compromise the leak detection sensitivity. Anywhere the cover material is providing a current path to the underlying material or to ground is going to behave like an actual leak. So us as electrical testers, we have no idea whether it's a leak or something else that's conducting the current. So as designers, you need to be cognizant of what could possibly cause current leakage from the survey area. If we can manage to create complete electrical isolation of the cover material, the only path the current can take is through leaks. And that's when you're going to get your maximum sensitivity. So there's two things that we need for applying the method. We need survey area isolation, and we need moisture. First, I'll talk about isolation. Here's a photo of a new landfill cell, and you can see that there's a gap that was created in the cover materials. The geosynthetics are intact in this gap. So there's liner and geocomposite or geotextile. It's fine for those to be intact. It's just the gravel and the soil-based materials that are kept away from that tie-in area. So this is what we call an isolation trench. It's critical for method functionality. So here's an illustration. This is the positive current injector electrode inside the new landfill cell, and we have a ground outside because this happens to be a single line landfill. We need isolation along every side of the landfill. Some people don't realize that even the tie-in needs isolation, every single area. This is an oddly shaped landfill expansion cell, but we need isolation along the entire perimeter. Even the access road, so usually the cover material is hauled from a location or locations. We need this cut, and ideally as dry and clean as possible. This is another isolation trench. We have the survey area on the left and the ground on the right. You'll notice there's a lot of piles of material here. It's very common to leave a windrow right outside this isolation trench because the contractor is going to eventually fill in that trench. Those piles of material are not an issue, especially if you have a larger dipole spacing. The thickness of the cover material should not exceed the spacing of the dipole. The dipole we use is 3 meters or 10 feet. So we can deal with piles up to 10 or 15 feet thick and have actually detected leaks under piles that thick. This is an anchor trench. You can see the geosynthetics are intact. Something like geocomposite and geotextile, they're not electrically conductive when they're dry. The problem with these is they can actually retain moisture when they get wet. So sometimes when there's a rain event, we might need to wait until these materials dry out. The other thing about these materials is if they get muddy, they're very hard to clean without cutting them back. So we have had some cases where they get so wet and muddy, we have to cut them back. We don't want to do that, so it's best to keep them clean and hopefully dry. But if it's just rainwater, that's something that can dry up fairly quickly in the sun. This is a LCRS trench. We do not want that rock in place. It's better to just not place that rock. See, it looks like they placed this and now it's quite dirty and they pulled it back after we told them we needed isolation. Much better to just not place that material in the first place. This is a tie-in area. See how much moisture is here? This is a very common site. A lot of the sites we perform this method on get rainfall every 3 or 4 days. So it's virtually impossible to keep this particular area, it's a tie-in area, it's virtually impossible to keep this perfectly dry. Well, the thing is rainwater is not conductive. When rainwater hits some mineralogy, it can pull off some ions and it can become conductive, but it's not super conductive. So this kind of isolation issue, it's not a deal breaker. We can usually manage something like this. The thing that's not good is when this is muddy. Rainwater okay, mud not so much. We strongly advise for the contractor to place a rub sheet under the access road so that when they do remove it for our survey, it's not that dirty. So they put this rub sheet down on top of the geocomposite so when they place the material, it doesn't fill in the geocomposite with fines. And so under this flap right here, the geocomposite is actually very dry. So it provides much better isolation for us. If we need to water during the survey, so we need an access road in place, you can always weld a little geomembrane flap along the access road location and then push the material up. So this geomembrane flap actually bisects the access road so that the road can be in place for the trucks, but it's actually electrically isolated. The photo on top here is a penetration in a stormwater pond. I surveyed this site and I saw this from a distance and I thought it was HDPE pipe. If I knew that it was ductile iron, I never would have surveyed like this. I actually started the survey and I had very poor sensitivity. Because the perimeter was really clean, I thought that my poor sensitivity was attributed to some large leak out there in the survey area that I had yet to find. So as I was surveying, I started picking up a leak signal and it led me right to this pipe. And I thought, what's that made of? Turns out it was ductile iron. So I stopped what I was doing. I had them excavate the iron pipe. There was a piece of wood here holding this up. So the geomembrane comes up this far on the pipe, and then all this is metal. And this piece of wood here was moist enough that it was still causing some interference. But anyway, I redid the survey, and this is the mapping from that project. This big leak signal down here is actually from that moist wooden block under the pipe. It's got a very large anomaly. It's about, you can see it from about 60 feet away. But fortunately, I was able to still pick up a little knife slice in this project. So at this particular project, yes, it disrupted the survey, but it really only compromised sensitivity locally to the penetration. For this project, every project's different. Sometimes something that large can mask leaks anywhere in the survey area. In fact, before we excavated that ductile iron pipe out and left that little wet wood in place, that ductile iron pipe was affecting the sensitivity of the entire survey area because my artificial leak was set up on the far distant half of the pipe, and the sensitivity was poor to begin with, and then I checked it again after we excavated the pipe and it was very good. So this is why we try to minimize the isolation issues. So we talked about isolation. The next most important thing in survey area preparation is moisture. This is the most common question I get is how much water do I add? How much moisture? What's the moisture content? How wet is wet enough? Unfortunately, it's not a simple answer. The answer is there's actually 3 different reasons why we need moisture in the cover material. The first reason is that the cover material itself needs to be electrically conductive. We don't usually need to add moisture to make this material conductive. Usually it's conductive enough at a natural moisture content. The highest moisture content we could possibly need is for something like sand, and it needs about 6%, but usually it's only about 1%. Very, very easy to attain. The other reason we need moisture is that if you have a very small hole, and especially if you have overlying geotextile or geocomposite, that hole is not going to be electrically connected to the cover material unless it's wet. So ideally, we want the survey area to have experienced rain recently, but if it hasn't, and all of those geosynthetics are dry above the hole, it really needs to be watered enough to actually cause the geomembrane to leak if you want to find those really small holes. The third reason we need moisture is that the surface will sometimes desiccate, depending on the material. Something like a clay or a gravel, they tend to desiccate in the sun. So it's weather dependent, it's climate dependent, but we need our probes to have good contact with the cover material. So when we come to site to test, the only reason we're going to ask you to water is if we can't get good readings through the surface. We will document the condition of the liner. We're going to dig a test pit down to the top of the geomembrane to place an artificial leak, which I'll be talking about next episode. And we're going to make observations on whether the geosynthetics are dry or not. But ultimately, we're not going to direct the moisture unless we can't read through that surface. If you can't drive on the cover material to water with a water truck, which is the easiest and most effective thing to do, you can also park the truck to the side of the survey area and extend hoses and water it that way. So that's what this photo is. You can see a dipole there and people moving those hoses around to water. If you can't access it via hoses, you can always just use these little water backpack sprayers. This is perfectly sufficient because we just need the surface wet where we're taking the data acquisition point. So keep that in mind, that we're not going to direct you to water any more than we need to read through the surface. But the truth is, if that geomembrane has not leaked in the past, then we might miss those little small leaks. So it's really easy to water the cover material before or during the testing, but the underlying layer, if it gets installed dry, there's no way to irrigate that after the fact. So it's really important to get that right. Typical subgrade is virtually never problematic. Again, it doesn't require a lot of moisture for a natural soil layer to be electrically conductive. It's only about 0.5%. And also, when that layer gets covered by a geomembrane, then the moisture tends to wick to the surface. The one scenario that is really problematic is when we have what I like to call an encapsulated geosynthetic clay liner, or GCL. What I mean by that is when you have a liner cross-section of, from bottom to top, secondary geomembrane, GCL, primary geomembrane. It doesn't matter whether or not there's geocomposite anywhere in those layers. But what happens is that the GCL moisture content is always conductive when it comes out of the factory because there is some moisture in there. But then when they deploy the GCL, it actually dries out in arid climates. If they don't cover it right away, it can sit out all day long and bake in the sun, and it can desiccate to the point where it's no longer conductive. We have seen issues with anywhere less than 8% moisture content. This is material specific. So every type of GCL is going to have a different cutoff moisture content. In order to determine what that is, you need to test it. So if this encapsulated GCL desiccates to below the moisture content where it's conductive, you have real problems if it's a permit requirement to test that primary geomembrane because the test is not going to work. In episode 6, we're going to talk about design solutions to these types of problems, but I just wanted you to be aware that it is potentially a problem. So let's talk about testing the primary geomembrane of a double line facility. This is one example of a cross-section that we might test. We have cover material, primary geomembrane. This particular cross-section has an encapsulated GCL, and then we have a secondary GCL. The problem with this cross-section for us for testing is that we need electrical access to the GCL layer because we need to connect our return electrode to this layer. So if it's desiccated, the current's not going to be able to make that loop. So what we're going to do is instruct you to insert electrodes into that layer. I like for them to be placed below the GCL to just kind of add extra weight to that. And we want at least 2 separate wires. See, we have one main wire for testing, and then we have this separate satellite wire that's completely disconnected from the first wire. Why do we need 2 wires? We need 2 wires so that we can do a check to make sure that that subgrade is sufficiently electrically conductive. If you have a leak location contractor who only asks for 1 wire to test this kind of system, that should be a red flag because there's no way to test for sufficient conductivity in that layer. They'll perform the test and hopefully it's conductive enough and it works, but if it's not, nobody will ever know. I'm going to take a quick detour and talk about what is unique to water-covered surveying. So this photo shows a water-covered wading survey. If the water is shallow enough to wade through, we can do a really good job with the dipole because we can carry the instrument throughout the survey area. This particular fellow is walking in a straight line across a survey area at offsets, so he's doing multiple transects. And he's reading the voltage as an analog value. So he can move that thing anywhere and acquire voltage values anywhere. He can go back and forth and he can pinpoint. If the water is too deep to wade in, we have to use what we call a remote drag probe. So there's a dipole on the end of a rope that we tow back and forth across the water. And it's just very imprecise. Not only that, but if you're reading the voltage as an analog signal and listening to beeps like this fellow is doing, it's impossible to get a picture of the entire survey area because in particular, the voltage values, it's very dynamic. You have areas of high voltage and low voltage. And the electronics will start beeping when you get an extreme of high or low. So you're constantly adjusting that range. So let's talk about water-covered wading surveys. They're extremely sensitive because even the smallest of leaks are actively leaking during the survey. You can pinpoint it exactly by moving that dipole back and forth and drop weight exactly where it is. The downside of this is there's no ability to isolate the leaks during the testing. For soil covered, we can locate a leak, we can excavate it, we can separate it from the cover material, and we can test around it because, as you know by now, large leaks can mask other nearby leaks. So you might have to retest this if you find extensive damage, especially if you find a location of large damage. So there's two ways to perform this testing using the dipole method. You can do real-time leak detection, where the analog voltage measurements are converted to an audible signal. And you can also do data acquisition or mapping. So the data acquisition or mapping is going to be the same approach as the D8265 soil covered voltage mapping that we're going to talk about in the next episode. The real-time leak detection per D707 is very similar to the bare geomembrane methods, where the instrument basically beeps when there's a hole. It's very operator dependent. As I said, it requires a more dynamic instrument adjustments, so it really requires a lot of expertise. And there is no document that's produced that allows the results to be reviewable. You're just trusting that the operator knew what they were doing, surveyed the complete area, and had the capability to find all the leaks. If you can add GPS to the water dipole, you have the best of all worlds because you can press the button as often as you want. The one positive of the analog voltage measurements where you're looking for the tone is that you can obtain as many measurements as you want. Well, the same is true when you have a GPS attached to the instrument. You can constantly press the button. In fact, we set our y-axis and then we just press the button all the time as we walk along those lines, so you can get really good resolution, plus you get a map at the end of the survey results. Now Sean is going to talk about factors in leak detection sensitivity. Him and I were working on putting this list together, and the more we talk, the more things we could think of. There are just so many factors in leak detection sensitivity for these methods, and I'm sure there are a lot more that we don't even know about yet. So with that, here's Sean.
Thank you, Abigail. Again, my name is Sean Kellendine, and I'm with Hydrogeophysics. Now we're going to take a moment to discuss factors in leak detection sensitivity for electric leak location surveys. This includes perimeter isolation, size and number of leaks, measurement density, material conditions in the survey area, and dipole spacing. The number one factor in maintaining good survey sensitivity for a successful ELL survey is understanding the survey area's electrical isolation needs. Electric leak location is governed by this really tenuous influence between the fill material's electrical properties, the resistive nature of geosynthetic liners, and the degree of electrical isolation obtained in the area to be surveyed. Now, we know electricity follows a path of least resistance, much like water flows through a pipe or in a river. This is the classic analogy useful for explaining Ohm's law and how these three variables interrelate. In a geosynthetic containment system, the material filling the reservoir is used to carry current throughout the survey area. A high-level electrical isolation will ensure that the current is available for the leak location process. However, we must consider that any electrical pathways in the survey area that are grounded to the outside world can bleed off electrical current needed for leak location. So it is critical to create a temporary electrical isolation state for the survey area to increase and maintain leak detection sensitivity. The level of electrical isolation will determine the difference between finding every hole or no holes at all. Again, with covered geomembranes, the material filling the system is what is used to carry current throughout the survey area. For a leak to be detectable, current needs to travel through the leak with an intensity that is significant and measurable when compared to all other current pathways available. Here In the top example, we show a survey demonstrating good quality electrical isolation. The leak within the survey circuit creates a strong current path between the current injector and the leak, allowing the operator to detect a high current density associated with the hole in the liner. Now in the bottom, however, there is a conductive bridge allowing current to escape from the survey area. In this scenario, a strong current path has been created between the current injector and the outside world. The bleed off of electrical current out of the survey area has now reduced leak detection sensitivity to a level below the sensor's ability to detect any leaks. In this particular case, the person doing the survey is blind to any potential holes that may be in a liner. Here is a personal example I had with electrical isolation. These images were taken at TRI's testing center in Austin, Texas several years ago. They show a classic real-world example of the relationship between electrical isolation and leak detection sensitivity. I'm using a dipole probe to find a leak in a liner on the picture on the left. I've actually found the leak, and the equipment is detecting the high current density associated with the hole. As the equipment gets closer and closer to the hole, a high-pitched tone gets louder and louder until it reaches a peak, indicating the hole's location. Then, on the right, a saturated piece of GCL is placed over the liner's edge, bridging the fluid inside of the survey area to the ground outside. When the GCL bridge was created, the equipment instantaneously stopped seeing the current, and the leak response was completely lost. The strong current path to the leak has been replaced by a strong current path to the GCL bridge. Now, once the GCL was removed, the strong current path returned to the leak in the liner, and we could now see the leak response again. Now, there are many other factors that are also significant for leak detection sensitivity. Conditions local to a hole, i.e. a leak, for example, must maintain good contact between the cover material and the subgrade. For example, if the material, the liner, and the subgrade is dry, and there is no electrical pathway between the material, the hole, and the subgrade, then there will not be a detectable electrical leak response. In order to locate leaks, a quality electrical pathway must exist between the cover material and the subgrade. Now, this is predominantly a challenge for soil cover systems and obviously not so much for water covered systems. Stainless steel and porous pots are also important. Equipment design matters. Stainless steel electrodes, for example, will polarize, creating an electrical burial potential that will increase noise and reduce signal if there's not enough available current to overcome the electrode's barrier potential and surface contact. Now, this does not mean that stainless steel electrodes can't be used. If the field material is significantly conductive and there is enough available current to overcome the electrode's barrier potential, then they will work. However, porous pots are a much better bet as they reduce noise through the direct transfer of ions from the material surface through a copper sulfate solution, making readings much more sensitive and accurate. This image shows an example of a porous pot. A porous pot is a non-polarizable electrode that allows the free flow of ions to the earth. The yellow container holds a copper rod in a saturated copper sulfate solution. The solution is wicked through a porous membrane, typically ceramic, and makes contact with the survey material. Ions flow between the material and the electrode, and measurements are made. Now let's look at how current moves through the material and why this impacts sensitivity and our ability to find leaks in liners. We are going to look at electrolytic conduction. Most earth materials can transmit electrical current. Now the rate of current flow is related to the material properties, i.e. is it resistive or conductive? Now electrical conduction is a function of the following: moisture, ionic strength, porosity, ionic mobility, mineralogy, and tortuosity. So where is electrical current flowing? Well, electrolytic conduction relies on fluid-filled pore spaces and available ions. That is the fraction of water filling the pore space, the fraction of ions available for current flow, and the fraction of pore space relative to solid grains. Now in this image, we have a blown up version of fill on a geosynthetic liner. We've got two examples. We've got clean sand and we've got clay-coated sand. But that's not all the scenarios we're going to see out in the field, right? We're going to see lots of different scenarios. Maybe you have gravel, gravel mixed with sand, river rock, river rocks mixed with dirt and sand. All different kinds of material go into these different systems. However, these two can help us understand the factors of electrolytic conduction and how they affect ionic mobility. So, clean sand. Let's say, for example, we've got a system where we've got clean sand as our fill material, and it's alpine, and some snow or some rain has rained on the system to wet it down. Now, if the snow and the rain is actually very clean water, which in alpine systems it tends to be, um, you end up with a really resistive situation. You might think it's conductive, but it's actually resistive. And that's because water is actually resistive when it's perfectly clean. It's the things in the water that make it conductive. So when you put on a resistive substance or fluid like clean water on sand, you're going to end up in a very resistive situation without very many ions to move through the system when they're charged by injecting current into the system. It's going to be hard to find a hole. With a clay-coated system or a dirty sand system or a dirty gravel system or something like that, when you put any kind of fluid on it, the fluid is going to mobilize the minerals in the system. It's going to mobilize the ions that are already there. And when you charge that system, ions are going to move freely to ground through a hole, and we'll be able to locate it. This is electrolytic conduction. So one of the most important factors for electrolytic conduction is moisture. If you're in a situation where your material is really conductive and dry, simply add water. It will increase your leak detection sensitivity. Survey direction can also matter. Note Figure A, survey direction north-south, where 5 leaks were located, and Figure B, survey direction east-west, where only 4 leaks are located. Leak signals in the field may be oriented so that stronger current densities may be present on the side of the leak closest to the current injector. In any case, if anomalies are difficult to tease out in one direction, changing directions may create a more sensitive leak response. It's important to keep in mind that surveying in 2 directions is not possible or cost-effective for every scenario. However, some leak detection equipment can survey in 2 directions at the same time. Furthermore, surveying in 2 directions may only be needed when anomalous data is present in a specific area, and changing directions might tease out additional leak responses. For example, the missing leak in example B was a small knife slice. They were able to tease out after changing directions. A larger dipole spacing also enhances the leak signal and increases the leak detection distance, even when applying the maximum measurement density prescribed by ASTM D7007. A 1 meter dipole cannot achieve the level of sensitivity of a 3 meter dipole at a 3 meter by 3 meter density. This does not mean that a 1 meter dipole configuration is not a valuable option. On the contrary, if space is limited due to site size, obstructions, or other space limiting factors, the 1 meter dipole system can be an important asset. Here is an example of measurement density and dipole spacing affecting the sensitivity of the dipole method. The larger dipole spacing results in a higher survey sensitivity at the same measurement density. Note the larger magnitude signal of a leak using a 3 meter dipole at a 1.5 meter by 1.5 meter measurement density. Another area is data analysis. Data processing and data analysis to confirm leaks and reduce false positives are a significant advantage to the leak location process, offering the highest quality results. The ability to map data and review the finer details increases survey management controls and understanding of data over the entire survey area. For example, were lines missed due to exhaustion or other challenges? Were data points missed, leaving potential leaks unfound? Did data quality change during the survey and go unnoticed during acquisition? Or could changing survey directions increase sensitivity to find more minor leaks or tease out a leak no leak response from anomalous data? Data analysis gives much greater control over the survey results and improves project success. Sensitivity and electrical isolation will also vary based on site conditions and structure configurations. For example, ponds may have more penetrations, electrical equipment, and more concrete features than soil covered structures. All penetrations, concrete features, and electrical infrastructure will need to be isolated to ensure the current is available for leak location. Soil covered structures are typically much more massive than ponds, with fewer liner penetrations. However, the large size may make it harder to maintain isolation along the boundaries, and precipitation could cause an isolation breach, bringing down sensitivity. Single and double line systems also present different challenges. With single line systems, the substrate the liner is on must be sufficiently conductive to carry current from a leak. Any grounded electrical infrastructure nearby could create excess electrical noise, limiting sensitivity in the survey area, and should be turned off. Secondary liners cannot be tested in double line systems, and the void space between the liners must be filled with water for the leak detection process to function. Depth of material on soil covered liners is limited to about 10 feet or less, while the depth of solution in ponds may be a few inches to tens of feet deep and require different styles of leak location equipment based on water depth. Finally, site response current is important and may be used as a quick test to determine a leak or no leak situation. Site response current is the current that flows through the cover material to the underlying conductive layer due to an applied voltage in the survey area. If a site has perfect boundary conditions for electrical testing, meaning that the only electrical pathway through the geomembrane is through any leaks present, then the site response current measurement could be used to alert operators of the presence of leaks in geomembranes. For example, high quality electrical isolation with no leaks will give you a site response current that will be low. On the other hand, low quality electrical isolation with no leaks may give you a site response current that will be high, as well as low quality electrical isolation with leaks. The site response current will also be high. In the best case scenario, you will have high quality electrical isolation with some leaks, and the site response current will be moderate, with the caveat here that depends on leak size. Remember, low quality isolation typically draws more current than actual holes, unless liner breaches in the system are huge. Site response current measurements can give important information on the conditions of both the liner and the survey area and could be used for quick accounting of a leak or no leak situation if electrical isolation of the survey area can be assured. This is great for quality control. For example, if the site response current is known for a zero leak condition at a particular site, a quick test could be performed consisting of simply a current response measurement. If the current flowing through the system at some point increases while the survey area remains isolated, then a leak location survey may be necessary. If site response current remains consistent through the system, then no new leaks are likely to have developed. This gives operators a quick and easy way to understand quality control and if their site is in good condition or if they need a leak location survey. We would like to thank everyone for attending our presentation today. And if you have questions, we'll take them right now.
Not necessarily water path, but electrically conductive path,
Right.
which usually means some amount of moisture.
Right. Yeah, so there's this, what we did talk about in that one particular slide, there's this idea of tortuosity, right? What is the actual pathway current is following. So if, for example, your current is moving through the material that has, really low moisture, but there's still ion flow and it connects through a hole, you're going to have a pathway. Now, if you add water to it, then that's just going to increase your sensitivity and give a better pathway through the hole to the subgrade.
Yeah, so in a double line system where the underlying conductive layer for your primary is a GCL, I like to install the copper wire just before the GCL goes down. If you do it after the GCL goes down, it's okay. I just like the extra weight of the GCL to be there because you want good contact between the copper wire and the GCL. But in any case, before the primary geomembrane goes down, you want that electrode installed.
I imagine this is something that you run into a lot, Abigail, as far as the timing and make sure engineer knows when to do this.
Yeah, and so just so you know, it doesn't make it impossible for us to do leak location if that electrode's not installed. What it does mean is we need to figure out how to gain access to that layer. So I test a lot of sites that don't plan for leak location. They know they're leaking because they're double lined. I come out and I just figure out where I can put my return. So I like to try to put my return as close as possible to where that liquid's coming out. So if they have a witness zone, a leak detection sump, I want to put it right in there and touch the liquid with it. And basically, if that hole is connected to the wet path, which it will be, that's where I want my electrode. Yeah, here's the thing with measurement density. It's meaningless to talk about measurement density if you're not referring to the size of the dipole.
Yeah.
The more important of the two is dipole spacing. And it's totally appropriate to do a grid spacing that's equal to your dipole spacing. So I agree. I would never perform a 3 meter by 3 meter test with a 1 meter dipole. That's crazy. But if I have a 3 meter dipole, it's totally appropriate to do a 3 meter by 3 meter spacing. So normally surveys are done in one direction, and the direction is pretty much, it's arbitrary. It's whatever's easiest to do. It's usually, I like the long axis. So you only have to run the survey in one direction according to both ASTM standards. We were just mentioning that as one of the factors in sensitivity, direction actually matters. It's not required anywhere by any standard. It's one of those things, you may or may not miss a leak because of the direction you choose, and there's really no way to know unless you survey both directions. And it's practically never done to survey both directions unless you have the double dipole equipment that does both at once. That way you don't spend any extra time doing it. It's like an extra measure that you get for no additional cost.
Yeah. And the other thing there too is that when you're in the middle of a survey, if you notice, strange anomalies or you're getting strange readings, you can, you can do different directions in that particular area to kind of increase your resolution and narrow down and maybe tease out, a leak or no leak situation, right? Because you may actually see something and you're not sure what you're seeing. So if you change directions, it might become more clear.
That's absolutely right. When we go back, we look at the map and we see a little weird anomaly, we're not sure what it is. We go back and we always change direction. Like, okay, you don't see it here, but do you see it here? And that's actually another way to weed out signals. So for example, when we cross a pipe, we sometimes get a blip as we cross the pipe. Well, we want to go back to that pipe and survey along the pipe. If we still get a blip, there's something under that pipe. I've found a lot of holes under pipes. That's a great question. I have found a lot of leaks in tie-in areas when the tie-in area is well isolated and wet. You remember that photo I showed where the tie-in was really wet? What we do is whenever we see a leak signal on there, we investigate and we visually trace the signal to see if it's coming through a hole or if it's coming from a grounded scenario. So some of the landfills I test actually have an isolation flat built into the tie-in, and we can fill that with water and test it very well. But for most conditions, it's going to be very hard to test that tie-in. So as a designer, if you're concerned about the tie-in area, which you should be, you might want to develop a companion specification for arc testing the tie-in while dry before performing the dipole test or something like that. But absolutely, the tie-in area for most dipole testing is not tested, or it's tested with difficulty. So it's a location where leaks can be missed if you don't have that additional spec to do arc testing or something like that. That is a really excellent question.
Yeah, that is. Abigail, you want to take that?
So yeah, it absolutely can be a problem with an
Yeah.
injector in return. And I have noticed this at some sites, especially sites where leachate gets in my circuit or I have weird mineralogy. My current injector is constantly reacting with my cover material. And so I'm observing the current all day, and it's driving me crazy because I want everything to be super precise, and I can't if the current's jumping all over the place. And so the thing you can do is you can sort of cushion the injector from the cover material by encasing it with something that's less reactive. You can also specify constant current so that your power output will oscillate the voltage while keeping the current the same. Still, you might hit a maximum or a minimum, but absolutely it's an issue. It's definitely a quality control issue, and I bet it's really an issue for a brine pond type solution, which Sean does a lot more of than I do. So,
Yeah. Yeah, basically you said it all right there, Abigail, so I don't need to add to that. It can. Yeah. So, I mean, it's all relative, right? So, how dry are we talking, right? So, I mean, is this completely desiccated system where you have little to no moisture in it, then yes, that could create an environment that is highly resistive and you wouldn't get a connection between your overburden through a hole to your subgrade. However, if there's even a tiny bit of moisture and you have ionic flow, then you should be able to see a leak. But always in any situation when you have dry material, the best case scenario is to wet it down. Wouldn't you agree, Abigail?
oh yeah, yeah.
Yeah, I think we talked a little bit about this last webinar, right? Talking about the circuit that you have to have the conductivity above and below the insulating geomembrane.
Yeah.
And there's
Yeah.
things you can do to improve the overburden, such as add water, and below adding copper wires, conductive geomembrane, other things to help the conductivity below.
Right.
We'll see you next time. Thank you.